Section 7.5, Hermitian, Unitary, and Normal Matrices. If A is a complex matrix, then the conjugate transpose of A, denoted by A star, is defined by the transpose of the conjugate of A. So how about we find the conjugate transpose of the matrix given in example 1. So first we'll find the conjugate, A bar. So instead of 1 plus I, we'll write 1 minus I. Instead of minus I, we'll write positive I. And instead of 0, we'll still write 0. Because we only put the minus in front of any of the imaginary parts, or we only adjust the sign in front of any of the imaginary parts. So 2 stays 2, and 3 minus 2i becomes 3 plus 2i, and I becomes minus I. So that's the conjugate of A. Now let's get the conjugate transpose, A star. So we'll just take A bar, and we will transpose it. So we get 1 minus I still on the top left, but then underneath it becomes I, and underneath that becomes 0. That's our first row, so that's our first column. And then our second column is 2, 3 plus 2i minus I. If K is a complex scalar, and if A and B are complex matrices whose sizes are such that the stated operations can be performed, then we have that A star star is A, so star cancels. A plus B star is A star plus B star, so you can distribute the star. Similarly for subtraction. K A star is K bar A star, so you just move the star over to the K by conjugating it. And A B star is B star A star, kind of like when we had AB transpose is B transpose A transpose. So the only one you have to be careful about is the multiplication distribution. A square matrix A is said to be unitary if A star equals A star A equals the identity, or equivalently if A star is A inverse. So it's unitary if its inverse is its star. It is said to be Hermitian if A star equals A. Let's determine whether the matrix given over here is Hermitian. So notice that we have 1 minus 5 and 3. Those are all real numbers. So in other words, they're in the set R, they're real numbers. But the other entries, if I look at, for example, I and minus I, those are conjugates. 1 plus I is conjugate to 1 minus I, and 2 minus I is conjugate to 2 plus I. So the other entries are conjugates. What that means is that when we take the conjugate, all of these guys will stay the same in the middle because they're real numbers. These guys will change signs, but it doesn't matter that they'll change signs because they're going to flip due to the transpose. So A is Hermitian. It will be equal to the same thing as if you take the conjugate transpose. How about we determine whether this matrix is unitary? So let's check whether A star is A inverse. Let's compute A star. So we only really have to worry about these guys. We'll take the conjugates and they'll just turn into pluses, and then they'll flip, but they're the same anyway. So really we get the same matrix, it's just all positive. So we have 1 over rad 2, positive 1 over rad 2i, positive 1 over rad 2i, and 1 over rad 2. Now let's get A inverse. So what we should do is get the determinant. So multiply those, we get a half. Multiply these, we get minus a half. Half minus minus a half is 1. So we just have to divide by 1. So that determinant's not going to change it when we divide by it outside. And then we turn these into pluses and we swap these, but they're the same. So yeah, A inverse will be equal to 1 over rad 2, 1 over rad 2i, 1 over rad 2i, 1 over rad 2. They equal each other, So yeah, A is unitary. If A is a Hermitian matrix, then the eigenvalues of A are all real numbers, and eigenvalues from different eigenspaces are orthogonal. Let's confirm that the Hermitian matrix in example 4 over here has real eigenvalues and that eigenvectors from different eigenspaces are orthogonal. So let's get the determinant of lambda I minus A to get the eigenvalues. So that's the determinant of lambda minus 2 minus 1 minus I minus 1 plus I lambda minus 3, which is lambda minus 2 times lambda minus 3 minus 1 minus I minus 1 plus I, and multiplying that out we get lambda squared minus 5 lambda plus 6 minus 2. We can combine the two and then factor and get lambda minus 1 times lambda minus 4. So if we set that equal to 0, we see that lambda equals 1 and lambda equals 4 are our eigenvalues. Let's look at the corresponding eigenvectors. So for the eigenspace lambda equals 1, we'll get minus 1, minus 1 plus 1, minus 1 minus I, minus 2. When we plug in 1 into lambda I minus A, and then we'll append a column of zeros, and we'll reduce this. Okay, so we can divide this by minus 1 to get a leading 1, and notice we can take 1 plus I times that to cancel this row and get zeros. So we have 1, 1 plus I, 0, 0, 0, 0 on the bottom, which means that x1 plus 1 plus I times x2 should be equal to 0. So I get an eigenvector x equal to minus 1 minus I times t over, and then t in the second component, because I just moved this to the other side. x2 is free, I set it equal to t. So that's actually the basis. Actually, I can get a basis vector out of that, so I'll get an eigenvector by factoring out t. And I'll get minus 1 minus I, 1. Let's look at the other eigenspace. So plugging in lambda equals 4, we get 2 minus 1 minus I minus 1 plus I, 1, and add a column of zeros. Setting it equal to 0 will reduce it, and the bottom row zeroes out again when we divide by the 2 for the top. We get 1 half minus 1 minus I, 0, and all zeros. So x2 is free again. We have x1 plus half minus 1 minus I equals 0, giving us x equals half 1 plus I times x2. I'll make that t for x2. Factoring out t, we get a second eigenvector equal to half 1 plus I, 1. Okay, let's take the dot product now to show that they're orthogonal. So we take v1, dot it with v2. We'll take minus 1 minus I times half times 1 plus I conjugate, because we have to do the conjugate for the dot product when it's complex, plus 1 times 1. And that'll be half minus 1 minus I times 1 minus I plus 1. And everything in there cancels and we get 0. So yeah, the two eigenvectors are orthogonal. If A is an n by n matrix with complex entries, then the following are equivalent. A is unitary if and only if the length of AX equals length of X for all X in Cn. AX.AY is X.Y for all X and Y in Cn. The column vectors of A form an orthonormal set in Cn with respect to the complex Euclidean inner product, and the row vectors of A form an orthonormal set in Cn with respect to the complex Euclidean inner product. As an example, let's use this theorem to show that this A given over here is unitary in example 5, and we'll find A inverse. So how about we use the one that says that the row vectors form an orthonormal set. So we'll check if the row vectors have length 1 and if their dot product is 0. So first out, how about we denote the first row vector by the first row? So that's half 1 plus I, half 1 plus I. And the second row vector will be R2. That'll be half 1 minus I. Oops, I wrote plus, need minus. And the other one is half minus 1 plus I. Let's get the length of R1. So that'll be equal to, we'll take each of the components, square them, take the square root. So we'll take half 1 plus I. We'll do the absolute value of that, and we'll square it, and we'll add that to the absolute value of half 1 plus I squared. And we'll take the square root of all of that. Okay, so we get that this length over here squared is a half. The other one's also a half. So we get the square root of a half plus a half, which is 1. How about for R2? So again, we'll do half, this time 1 minus I, which I keep writing as plus for some reason. Okay, so 1 minus I, we'll take that absolute value, square it, add that to the absolute value of half minus 1 plus I, squared that, take the square root, and we get half plus a half again, square root that. So square root of 1 is 1. So they are normalized. They have length 1. Let's see if they're orthogonal. So we'll take R1 and dot it with R2. So that's half 1 plus I times half 1 minus I, and we'll remember to take the conjugate. Add that to the next components, half 1 plus I, and multiply that by the other component conjugate, so that's half minus 1 plus I. Okay, let's keep going. I'll rewrite it with applying the conjugate, so half 1 plus I times half 1 plus I plus half 1 plus I times half minus 1 minus I. And notice that'll be half I minus half I, which is in fact 0. So because the row vectors form an orthonormal set, that's equivalent to A being unitary. Beautiful, so we just proved A is unitary. So now that means that we can get the inverse by finding A star, because it must be equal because it's unitary. So A star in this case is just, we'll take the conjugate, take the transpose, so half 1 minus I, half 1 plus I. These two will swap. So even though minus goes over here, it exchanges with this one over here. and this minus becomes a plus and swaps over, so they end up staying the same on the diagonals. So half 1 minus I, and then on the bottom we just have to conjugate that, and we get half minus 1 minus I. So it's pretty fast to find an inverse if you know that your matrix is unitary, and you just take the unitization, I guess you could say. A square complex matrix is said to be unitarily diagonalizable if there is a unitary matrix P, such that P star AP equals D is a complex diagonal matrix. Any such matrix P is said to unitarily diagonalize A. Every n by n Hermitian matrix A has an orthonormal set of n eigenvectors and is unitarily diagonalized by any n by n matrix P, whose column vectors form an orthonormal set of eigenvectors of A. So using that theorem, we can find a matrix P that unitarily diagonalizes the Hermitian matrix given over here. Okay, by example 4, we saw that lambda equals 1 gives us an eigenvector of v1 equal to minus 1 minus I 1, and for the eigenvalue lambda equals 4, we get the eigenvector v2 equal to half 1 plus I 1. So what we need to do is find the length of each of these guys so that we can get them normalized. So the length of v1 is equal to absolute value minus 1 minus I squared plus 1, take the square root, so that's square root of 2 plus 1, which is square root of 3. The length of v2 is equal to absolute value half 1 plus I squared plus 1, take the square root, and that'll be square root of a half plus 1, which is rad 3 over 2, or square root of 3 divided by 2. You make sure the square roots in both, because usually when we say rad 3 over 2, we just mean the top. But let's write our new vector P1 for our new matrix P equal to the orthonormal eigenvector, so that'll be v1 divided by its length, because this is how we diagonalize. We have to have an orthonormal set. So we have minus 1 minus I over square root of 3, and we have 1 over square root of 3. We can also get P2. That'll be v2 divided by its length. So that's equal to 1 plus I over rad 6 and 2 over rad 6. Okay, so our matrix P is built out of P1 and P2. So it's just minus 1 minus I over rad 3, 1 over rad 3 for P1, and then 1 plus I over rad 6, 2 over rad 6 for P2. So this means that we have P star AP equal to minus 1 plus I over rad 3, 1 over rad 3, 1 minus I over rad 6, 2 over rad 6, that's the conjugate transpose for P, and then multiplied by A, 2, 1 plus I, 1 minus I, 3, and then multiply by the P we obtained originally, so minus 1 minus I over root 3, 1 plus I over root 6, 1 over 3, 2 over root 6, and you can actually do the multiplication if you want, or you can just, I don't know, trust or believe that it actually will have a diagonal matrix with the eigenvalues along the diagonal, zeros otherwise, because it's diagonal, and it's that's the matrix P that unitarily diagonalizes this Hermitian matrix. A square real matrix A is said to be skew symmetric if A transpose is minus A, and a square complex matrix A is said to be skew Hermitian if A star is minus A. So it's like almost Hermitian. Matrices with the property AA star is A star A are said to be normal.